Thank you very much, Caitlin, and thank you for the invitation. It's a pleasure to be here and to see some familiar faces. We don't have this opportunity very often in Australia these days, but hopefully we'll be in person soon. So I'll talk about shell effects in two types of reaction mechanisms. The first one is fission, which occurs when you have a heavy nucleus which splits in two lighter fragments. And the second reaction mechanism is quasifission, which occurs when you have a collision of two heavy nuclei. So a priori, two very different mechanisms, but we will see that eventually we can connect the shell effects which influence the formation of the fragments in both mechanisms. So as a disclaimer, I should say that I will only talk of shell effects responsible for the formation of the fragments, and in particular responsible for their final number of protons and neutrons and shapes. I will not talk about shell effects which could occur at earlier stage in fission, for instance, in the compound systems. So I will only focus on the late shell effects at the very end of the fission mechanism. So let me start with fission. Fission was, as you know, is known since a long time. It's about more than 80 years now. And it was discovered by Otto Hahn and Lise Meitner. So Otto Hahn, by bombarding uranium with neutrons, observed the formation of barium. And that was later on interpreted by Lise Meitner as a fission, so as a splitting of the uranium in two lighter fragments. And you can see already that at the very discovery of the mechanism, the fission which was observed was already asymmetric. And that we can only explain thanks to shell effects. Without shell effects, we would expect the system to split in two symmetric fragments. So if you look at the fission of uranium, you have two groups of fragments, there is a distribution of heavy fragments and distribution of lighter fragments. So if you take the centroid of these distributions and you repeat the process for other actinides, what you get is a distribution of centroids for the heavy and lighter fragments. So far, there is about 30 actinides which have been measured with neutron-induced fission. And what you see is that the heavy fragments are always located in the same region of the nuclear chart, while the lighter fragments are basically distributed with a complementary fragment. So you expect shell effects to be quite important or dominant in the heavy fragment. So, of course, you could ask the question if the shell effects are mostly protons or neutrons. I mean, you can have both, of course, but one may be stronger than the other. And this was, I think, is understood since about 20 years now, since the experiments at GSI by Caroline Schmidt and collaborators. So they looked at systematics of neutron deficient actinides, so by varying the number of neutrons. And what they saw is that the heavy fragment is always formed with the same number of protons, so centered around 54 protons, while the number of neutrons will vary. So it's likely that shell effects are dominantly present in the Z equal 54 region due to the protons. Again, that doesn't mean that there is no shell effect in neutrons, but those in protons seems to be more important. So Z equal 54 is not far from Z equal 50, which is a well-known spherical magic gap. And we could think of mechanisms which will explain why we get 54 protons influenced by a shell effect at Z equal 50. For instance, you have a spherical core plus some nucleons in the neck, which are shared between the fragments. So, however, if you look at the distribution of fragments, of the distribution of the number of protons in the fragments for different actinides, you see that this distribution is basically ranges from 52 to 56, 58. And there is very little events at z equal 50, despite the fact that it's a magic number. And in addition, I think even more striking is the observation in the neutron-rich fermium of a very rapid change of the mode of fission. So for fermium 258, you have a very symmetric fission with a narrow peak, while if you remove two neutrons, you end up with an asymmetric fission. So the symmetric fission in fermium 258 is interpreted by Z equal 50 shell effect, because fermium has 100 protons. So if you split it in half, you have two Z equal 50 fragments. And you see also that there is a large tail for this system. So in fact, what's interesting is if you look at the total kinetic energy, you see that there are two modes present in this system. And the total kinetic energy is a kind of a proxy for the shape of the system at scission. So the more compact the system is, the larger the total kinetic energy. And by playing with gates in the analysis of their experiment, Hewlett and collaborators showed that higher TKE correspond to the symmetric mode in fermium 258, while the lower TKE correspond to the tail, which is in fact an asymmetric fission, a bit similar to the one you have in fermium 256. And in this one, what you have is a heavy peak, which is around Z equal 54, 55. So it indicates, just by looking at experimental data, that you have two modes in presence. One where you have a strong influence of the Z equal 50 spherical gap, and another mode. And if it is another mode, you will expect that it comes from other shell effects. So partly to investigate this physics, we did some theoretical calculation. We started that about a bit less than 10 years ago now. And the approach we followed is based on the Hartree-Fock theory and its extensions. So the Hartree-Fock, so I just have one or two slides about theory, and then I will talk about results. The Hartree-Fock theory assumes that you have independent particles which evolve in a mean field produced by the ensemble of particles. So it's very simple, but it's self-consistent because the mean field depends on the state, the entire state of the system. Usually you add on top of that some pairing correlation to account for the fact that the nuclei have some superfluidity in them, and this superfluidity has an important impact on the fission mechanism. So you do that with either the BCS approximation or the Hartree-Fock-Bogolyubov, which is more general. It's also, if you stay at the mean field level, usually you can only get average quantities. So for instance, if you look at, you can get the position, the centroid of the fragments. That's a kind of quantity which is within the range of application of Hartree-Fock and TDHF. However, you will not expect to be able to describe the width of this distribution. For that, you need fluctuations beyond the mean field. So for instance, with the stochastic mean field approach, there's a time-dependent RPA. And if your method is based on potential energy surface, you can use the time-dependent generator coordinate method or solve the Langevin equation. So all these methods have been developed and applied by recent groups recently. I'm not going to need to go beyond mean field in today's discussion, all because to discuss shell effects, just the position of the peaks are sufficient. An important point to note perhaps is of such a calculation in terms of parameters, if you wish, is what describes the interaction between the nucleons. And that's done with an energy density functional, usually with Skirm, but we also have some time calculation with Goni interaction, and there are others on the market as well. But what's important is that there is, once you have an energy density functional, which is usually only fitted with structure properties like masses, radii, you can't really change any parameters. And usually there is no information coming from fission or from dynamics or from reactions. Therefore, in that sense, it's a kind of a parameter-free theory. So we usually have, we use a two-step method where we have first a static description, a static step to describe the early stage of the fission. And then in the later stage, we have a time-dependent evolution. So I will try to explain why we have this two-step approach. So in the static step, we solve the constrained Hartree-Fock equations. And so what we do is we constrain the quadrupole moment, which measures the elongation of the system, and also the octuple moment, which measures more its asymmetry. And for each set of Q2 and Q3, you solve the equation and you get a minimum of energy. And from that, you can describe a potential energy surface and describe, for instance, the fission valleys. So you have, in this case, for uranium, you have an asymmetric fission valley. And you can also see that there is a symmetric one. So in principle, you can do your calculations entirely at using this static method by pushing Q2 to the point just before the system breaks, so just before scission. However, there is an advantage of using a time-dependent evolution for the later stage. First, you include some potential non-adiabatic effects. So if you ski, for instance, and you ski downhill, you don't necessarily take the same path as you will take if you were walking. That's because of the dynamics. You have some velocity. But another reason why we use time-dependent approach is the time-dependent evolution works before and also after scission. So it's still well-defined after scission. So you see here, for instance, you have two fragments which are well-defined and will move due to their Coulomb repulsion. So once you have well-defined fission fragments like that, it's very easy to calculate the number of protons and neutrons in the fragments. And also because you have the velocity, you get the total kinetic energy. These are quantities which are a bit harder to extract from static calculation because typically you will have to stop the calculation before scission and have some criteria to define your neck and to count how many neutrons you have on each side, and then have some also criteria for the total kinetic energy. All right, so here is an example of a calculation for plutonium-240. So that was done by Guillaume Scamps. And so that's a nucleus which is after the fission barrier. And I should have mentioned also that we don't, perhaps I should also say here that we don't start from the compound system, the time-dependent evolution. Ideally, you would like to start from to do everything with the time-dependent approach. The problem is that because we are at the mean field, we don't have enough correlation to, in particular, to overcome the fission saddle point. So we start after in the fission valley, and we let the system evolve. So without any additional boost, or we just have a time evolution. And that's what you see here is the evolution of the density of the plutonium-240 forming two fragments, which after scission you see have very different shapes. So we performed similar calculation for a bunch of actinides, which were measured experimentally. And what we did was to check that our calculation will not depend too much on where we start in the fission valley, We started from different points, different elongation. And that's why in the vertical lines you see here, you have several vertical lines. Each of them correspond to one TDHF calculation with a different initial condition. So you have some fluctuations, typically 2 up to 3 units, 3 protons, but essentially you always end up with fragments in which correspond very well to what is observed experimentally. So that's quite encouraging. And if you look at the neutrons as well, so you plot for these, all these calculations, the number, the fragments in the nuclear chart. So these are each point here. And if you compare with the centroids of the experimental distribution, you see for the heavy fragment, there is a very good matching. And of course, if you get it right for the heavy, you get it right for the light as well. So what it means is that whatever the shell effects are, they are clearly present in the calculation. So you just need to extract them. So to do that, as I said, we focus on shell effects in the fragments. So we look at the system just before fission. And so what you notice, and that's not a surprise, is that both fragments exhibit some kind of pear shape. That's because you have, they have a Coulomb repulsion, a long-range Coulomb repulsion, but they still have this nuclear attraction in the neck, which induce a deformation in the neck and then gives them this pear shape. And you see that in all the systems, of course. And in particular, if you look at the heavy fragment, you have a very scientific demonstration of what I just said with all these nice pear shapes. So there is nothing really surprising here. That, as I said, it's just a hydrodynamics. The nuclei do not have the choice but to have fragments with a pear shape near fission. That's as simple as that. However, what's interesting is to connect this pear shape with what is observed recently and was already predicted a long time ago, that barium 144 and 146 have octuple deformation even in their ground state, and these are typical fission fragments for actinide. So let's see a bit more in detail why this is connected and why, or at least we think is what explain this Z equal 54 business. So what you see here is a potential energy surface for barium 144 calculated with constrained Hartree-Fock and BCS. So we observe that there is a ground state which has an octuple shape, so a pear shape. And again, that's not new, that was known well before. But what's really interesting is not necessarily the fact that the ground state is has a pear shape, but the fact that you have a broad range of octuple deformation, which can be achieved without too much energy. So you don't need to give too much energy to the system to give it some pear shapes or octuple shapes. And that's important because that's what we think explain why these fragments are produced preferentially. We just said that at fission, you have no choice but to have the system which acquire pear shape. So naturally, if you can produce one fragment, potentially two, with pear shapes which will not cost too much energy, the system will choose to do that. So if you look at the energy basically along this line as function of the octuple moment for different nuclei in this region, you see that for these nuclei, these fission fragments, you indeed have a broad range of octuple deformation for which the potential energy is flat. So you can deform them with no or little cost in energy. The fact that the ground state is oblate here doesn't really matter. What matters is the fact that you need to have something more or less flat. However, if you look at tin 132, so that's a doubly magic nucleus here, it's very hard to deform. So, and remember that you need to have this pear-shaped adhesion, and therefore this kind of, the fact that the tin 132 is very rigid and doesn't like to have energetically these pear shapes, hinders its production. Now, of course, because it's doubly magic nucleus, the Q value will be so large that you can still have its production and due to shell effect, but the fact that it's hard to deform hinders its production as well. So microscopically, what is the origin of these pear shapes? Again, that's not something new. That was well known. If you follow this red line, what you see is first the disappearance of the Z equal 50 gap, spherical gap, and instead you have two new gaps which appear, octuple gaps at Z equal 52 and 56. And so that explains why the centroid is around 54 for the heavy fragments, and also probably why you have a broad distribution from 52 to 56 and perhaps even higher. Okay, so so what happens to Z equal 50? Can we still have an, I'm sorry, I need some water. Can we also see signature of Z equal 50 in this calculation? So yes, we can. In fermium 258, it's actually the main mode we would observe. So this calculation, which are shown here, is for fermium 256. This one is mostly asymmetric. So you have potential energy surface, which show that the asymmetric mode dominates, and in particular producing barium 144. But there is also a shallow, you don't really see with the color code, but there is a shallow symmetric valley, which produce two tin 128 fragments. So on the right side, you see in the top the shape of the system at scission, just before scission, for that asymmetric valley and for the symmetric one. And just below it, you have the calculation, constraint Hartree-Fock calculation of the fragment themselves with constraint on the multiple moment to reproduce what we see at scission. So these are two independent calculations with constraint on Q2, Q3, Q4, Q5, and Q6 to reproduce these fragments. And this, in doing that, we have then access to the single particle levels in the fragments, so which are shown in blue for the neutrons and in red for the protons. And that's near the Fermi level. So the occupied levels are in dark colors, and when you have only a partly occupied level, you will have a smaller band here. So anyway, what you see is that for the symmetric mode, for instance, you have a clear shell gaps at Z equal 50 and N equal 82. So due to the shell effects in the tin 132. However, the dominant mode in this case is not Z equal 50, it's Z equal 56 and N equal 88, and also Z equal 44 for the complementary fragment. So this really illustrates that you have two competing shell effects in the production of fission fragments in the actinides. What am I doing this time? So I'll stop here for the fission part. And there is a lot of regions which are under study these days, experimentally and theoretically. There is a mercury region or the sub-lead region, and also the lead region with a lot of experiments and calculations, interesting calculations looking at shell effect in this region. There is also, I just discussed the actinides, but there is also the neutron deficient actinides, in which there is a transition between symmetric fission and asymmetric fission, which is would be interesting to explain. And there is super heavy elements which have interesting new modes predicted by theory, like super asymmetric fission modes. However, the problem here, and also for nuclei at the end of the R process, is that you can't really measure them. So that's mostly relying on theory at this day. The R process is important because the fission which occurs at the end of the R process induces a fission recycling mechanism, which then has an impact on the abundance of elements in the nucleosynthesis. But for the super heavy element and the R process, well, we just don't have experimental data. The problem with super heavy elements is that you can form them in experiment, but usually you tag them with the alpha decay. So if they decay via alpha emission, they don't fission. So it's hard to know what are their fission modes. So we don't know what the fission modes in super heavy elements are. I'll come back to that a bit later when I will talk about quasifission, because there might be a way to investigate shell effects in super heavy elements, but using, shell effects in fission mode of super heavy elements using quasifission. All right, so what is quasifission? Quasifission occurs when you have collisions of two nuclei, usually two relatively heavy nuclei, and when there's a mass transfer from the heavy to the light one. So this is an example of TDHF calculation, which was made by Kyle Godby. This is out of plane, so that you probably so what you see is that you initially had, I forgot to say that this is initially calcium 48, and this is a uranium 238, and the reaction plane is a YZ, so it's slightly out of plane. All right, so you have this mass equilibration process which occurs in quasifission, and which takes typically 10-20 zeptoseconds. So typical characteristic time of quasifission are 10-20 zeptoseconds. So what is plotted here is a result of TDHF systematics, a comparison of many TDHF calculations. And just to give you an idea, each point can easily take days, if not weeks or even months, to compute on supercomputers. So we are really talking of heavy, demanding computational calculations here. So what is plotted here is the fragment mass asymmetry normalized. So what it means that when you have in the entrance channel, you have an asymmetry which is 1. And if in the exit channel you have 2 symmetric fragments, you will end up with an asymmetry which is 0. And what is shown on the x-axis is a contact time. So how long the system are in contact before they reseparate. And you see that most of the reseparation occur in the 10-20 zeptoseconds characteristic of quasifission. You also see that very few of these quasifission reactions lead to actual full symmetry. And what happens is usually shell effects stop the mass equilibration during the quasifission process. So I will illustrate that with a couple of reactions, which we have studied theoretically and some of them also experimentally. So the first one is calcium 40 on uranium 238. And what you have here in the exit channel often is the formation of heavy fragment with about 82 protons. So that's characteristic of the magic gap for lead. And so this is just one calculation, but when you perform a series of calculations at different energies, different orientations, and different angular momentum, so that's you get a systematic of results. And I don't want to go into the details, but essentially what you want to see here is you have a lot of fragments produced with about 82 protons. So that's this line here. So clearly there is that sign, the shell effect, in the production of the quasifission fragments. So there was indications of these shell effects already from earlier experimental measurements, but which were only looking at the number of, at the masses of the fragments. So it's hard to really point, to prove that you have a shell effect when you have only a measurement of the mass. So you really want to measure the Z and the N, the number of protons and neutrons, in order to really characterize the shell effects. So for this reason, a few years ago at the ANU, we had a collaboration with Ganil, IPN, and CEA. And so what we did was to complement our detector, our cube detector, which measures the mass of the fragment, with X-ray detectors, which were brought by Ganil and IPN, I think. And with the X-ray, you can measure the charge of the fragments. So in combining both informations, we could indeed confirm the role of shell effect Z equal 82 in quasifission. So that's shown by this figure where you see a peak at Z equal 82. So we have shell effect in quasifission. We looked at other systems theoretically. Calcium-48 on Berkelevium-249 is one which we studied because it was the reaction which was used to produce the super-heavy element Z equal 117. And so these are calculations which were performed by Kyle Godby and Said Umar. And again, each of these points is weeks or months of CPU time. Luckily, you can run them in parallel. So what is plotted here is the final angle of emission of the fragments versus the number of protons. And what you see essentially is a band for the light fragment and for the heavy fragment, which indicates that you have very strong shell effects. So, however, when you draw a line at Z equal 82, you see you're a little bit off. So that doesn't mean Z equal 82 doesn't play a role, but that means that there is likely to have at least something else driving the system a little bit away from it. So if you look at the neutrons, you have also N equal 126, which is not far, but also a little bit off. However, in the light fragment, you have N equal 56, which is again due to the octuple correlations, but now for the neutrons. And it seems to have an importance in the fragments produced at backward angles. All right, so, but all these shell effects which we are talking about now in quasifission, they correspond. What we would like to do is to compare them with shell effect in fission. The problem is that if you look at the compound system, they are always super heavy systems, and we don't know what are the fission mode of super heavy nuclei. So for this reason, we decided to look at lighter systems, actinide systems, where we know what are the shell effects, we know what are the fission modes, and we want to look at their quasifission modes, if we can describe them with TDHF, and compare between fission and quasifission. So as an example, here is thorium-226. And the reason why we choose this system is it's a neutron deficient thorium, which is at the transition between asymmetric fission and symmetric fission. And that's why you have in its potential energy surface two valleys. You have the asymmetric valley, and you have also a symmetric one here. So the question is, if you try to produce this system with a heavy ion collision, you will have a lot of, you expect to have some quasifission. And will this quasifission produce the same fragments, so in the same valleys as the fission one? So that's the open question. It's important to notice that when you do in a quasi-fission reaction, you don't produce the compound system, right? You don't have the compound. It's not a fusion. Yes, there is no fusion. So quasi-fission occurs without production of the compound nucleus. Nevertheless, you still have a damping of the kinetic energy and some equilibration which occurs, which could potentially put the system into the fission valleys, which are the same as the one of the compound system. All right, so a possible reaction to look at is calcium 50 on ytterbium 176 above the barrier, typically 10% above the barrier. And keep in mind that the asymmetric fission here will be associated to a heavy fragment around 54 protons. So these are very recent calculations, so I didn't have time to make a movie with them. But essentially what you see here is in blue, the initial condition. So you have the calcium 50 and the ytterbium 176. Again, we looked at a lot of different orientations and impact parameters. This is just an example. And in red, this is the outgoing fragment. And the lines correspond to the center of mass of the fragments during the evolution. So you see that you definitely have a significant amount of transfer in these nuclei. This is a relatively light system, so it was not clear whether or not TDHF will be able to have quasi-fission in this system. And it turns out that yes, this is typically a quasi-fission reaction. You have more than full rotation. So it's a relatively long quasi-fission process. So in this plot, we look at the final number of protons and neutrons in the fragments. And we see in particular that the number of protons in the heavy fragments for long contact time, so for reactions which have significant amount of rotation before separation, you end up with fragments about 55 protons. So very close, or actually similar to what you have in fission. So that's an indication that the shell effects which stop the equilibration process seem to be the same as the one as in fission. So you can estimate how much of these fragments are produced, because in the calculation you can run different impact parameters and all the orientations, and you can integrate. And from that you can extract cross sections. So these are plotted with a red line from TDHF. So these are TDHF quasi-fission cross-section predictions. And compared with experimental fission yields, so not quasi-fission, but fission yields measured at GSI. So first thing is to notice is that you have a broader tail, a bit more asymmetric events. I mean, you have so much very asymmetric events in quasi-fission, but they are due to these events here, which are still in the process of undergoing equilibration. They are not yet stopped by a shell effect. Those which are stopped by a shell effect are typically found here, and they correspond to this asymmetric mode of thorium-226 fission. You also see absolutely nothing in the symmetric valley. So that's an interesting observation. And in the bottom plot, another interesting quantity you can look at is the total kinetic energy. So remember that total kinetic energy is a kind of a proxy for the deformation of the system at scission, and in particular, if it is compact or elongated. So that will be influenced by the shape of the fragments and their shell effects. So for the system which are still undergoing equilibration, we don't have a very good agreement between the quasi-fission calculation and the fission measurements. However, for the system which are stopped by the shell effect, we have a very, very good agreement between the fission experiment and quasi-fission calculations. So that means that clearly the same, I mean, not clear, but it's a strong indication that the same shell effects are found both in asymmetric fission and in quasi-fission for this system. In this plot, I'm showing, so we can do the same thing as what was done at GSI by looking at different, a chain of compound nuclei. So in GSI, this is what is shown on the right, and what I showed before. You have, they looked at fission in neutron deficient actinides, and they found a lot of, that all the heavy fragments were located around Z equal 54, while the number of neutrons was just varying with the system. So here, what I show is calculations for quasi-fission now, not fission, quasi-fission, for reactions involving a chain of calcium, so from calcium 40 to calcium 56 on ytterbium 176. So that's the beauty of doing theory, is that you can run things which are not yet, cannot yet be done experimentally, but hopefully in the near future, there will be neutron-rich calcium beams able to look at this system. So we do that slightly above the barrier. And that form, if it were to fuse, that will form compound systems, neutron deficient thorium from thorium 216 to thorium 232. And again, because only the fragments, the quasi-fission which have a long contact time are those which are stopped by shell effect. So I only look at the number of protons and number of neutrons in the heavy fragment for reactions which have about 20 zeptoseconds or longer contact time. That way, I'm sure the reaction has been stopped by shell effects. And what we find is, as in fission, constant number of protons of about 54 in the heavy fragments, while the number of neutrons just vary with the number of, with the system. So again, quite encouraging in the sense that it shows that fission and quasi-fission have similar shell effects. That brings me to my conclusion. Might have been a bit faster than what I expected, but that's life. So I first looked at shell effect in fission, in the fission fragments, not in the entire fission process, just in the fragments. And we saw that there is clearly evidence for spherical shell effect in the neutron-rich fermium isotopes. So these are spherical Z equal 50 and N equal 82 gaps. But for most of actinides, the asymmetric fission mode can be explained thanks to octuple gaps in Z equal 52, 56 region, and also N equal 88. And I didn't discuss that, but there is also calculations and experimental evidence for different modes in lighter systems. So in sub-lead and near-lead region, there is N equal 56, which could explain, for instance, the asymmetric fission of mercury 180. So this is an octuple gap, but for the neutrons now. But it seems that this region is also strongly influenced by proton shell effect, prolate shell effect in 34, 38 region and 42, 46. So here I give some recent reference of experimental studies which looked at these evidences for these effects. In the second part of the talk, I discussed shell effects in quasifission. So we first looked at, I would say, standard quasifission reactions, the one which will produce a super heavy nucleus if they were to fuse, because these reactions are simply strongly dominated by quasifissions by far, by orders of magnitude compared to fusion. And here what we have evidence, both theoretical and experimental evidence for Z equal 82, and also N equal 56 seems to play a role, at least in some systems, which is an octuple mode. But in order to connect shell effects in fission and quasifission, we looked at lighter systems which form actinide compound nucleus. And we found a strong evidence for similar shell effects as in fission. So, which in the case of fission, we interpreted as Z equal 52 and 56 octuple gaps. So, if they are the same shell effects, they should be the same explanation. Now, that brings me to a possibility for perhaps getting access to some information on the fission modes of super heavy elements. We know that it's very hard to produce these super heavy elements and even harder to look at their fission modes, at least with current techniques. However, if we believe that the fission modes are the same as in quasifission, we can simply look at quasifission modes, shell effects in quasifission forming super heavy elements, in reaction forming super heavy elements, because these ones are much, much more probable by orders of magnitude larger cross sections than the synthesis of super heavy elements, or even the formation of a compound system. And finally, I would like to thank my collaborators. So I probably forgot some of them, but these are the ones who contributed at some level to this, the results I have presented. There is Guillaume Scamps, Kyle Godby, and Saïd Umar. And at the ANU, we have David Hine and Nanda Dasgupta, who are experimentalists. And in the theory group, we have Rémi Bernard, Patrick McLean, and Wayne Lau. Thank you very much.